Hi, this is the fourth lesson of topic 6 on radioactivity. And in this lesson, we're going to learn about nuclear decay equations. And this leads on from the last lesson on radioactivity and the different types of radiation. Now, before we move on, let's quickly recall some of our topic 1 chemistry knowledge. This is the symbol for an electron. But what do these two numbers mean? We have one on top and one on the bottom. Pause the video and think. So the number on top is the mass number. The number on the bottom represents the atomic number. But it also shows us the charge. And as we know, the mass number is the number of protons plus the number of neutrons. And the atomic number shows us the number of protons. Now, in the last lesson, we learned about a few types of radiation. We learned about alpha, beta, and gamma. Pause the video and see if you can remember the mass and atomic number for each of these types of radiation. So, alpha particles have a mass of 4 because it has 2 neutrons and 2 protons, and an atomic number of 2. This is a helium nucleus, and because it's a helium nucleus, it doesn't have any electrons, it only has protons. Therefore, it has a charge of +2. Beta particles are essentially electrons, which have no protons and neutrons, but 1 electron. So our charge is -1. And gamma has no protons, no neutrons, or electrons. So it's 0, 0. Now a beta minus particle is an electron. A beta plus particle is known as a positron. You don't need to go into much detail. Now let's take a look at a nuclear decay equation. Here we have an example of alpha decay. We have a very heavy uranium nucleus on the left. And this uranium nucleus decays into a thorium nucleus and it emits an alpha particle. It's really important to note the mass on the left-hand side, which is given by the mass number 238, is equal to the mass on the right-hand side, which is equal to 234 plus 4. Now you should have realized this also applies to the atomic number. The atomic number on the left-hand side is 92, and that's equal to 90 plus 2. So the mass number and the atomic number is equal on both sides of our equation. So we can think of this arrow in the middle like an equal sign. Therefore, to balance nuclear equations, there are two things we need to consider. The first is the total mass on both sides of the equation and the total charge, or the atomic number. Let's take a look at a few more equations. On the top, we have the alpha decay equation we looked at before, where a uranium nucleus decays into a thorium nucleus and an alpha particle. Try the one on the bottom. Pause the video and have a go. So, if we follow the hint at the bottom, always try to fill in the decay particle first. And as we can see, the mass number of an alpha particle is 4. This nicely satisfies our equation of 234 plus 4 is equal to 238. Now let's try the atomic number. We have 94 on the left-hand side, and at the moment we have 2 on the right-hand side. Therefore, for this to be equal, our atomic number for this uranium isotope is 92. So during alpha decay, the mass number decreases by 4 and the atomic number decreases by 2. And that's what we see here. What about this one? This is an example of beta decay. Try and fill in the blanks. So, as we know, for a beta minus particle, our mass number is 0. And this lines up with our equation as we have 14 is equal to 14 plus 0. Then if we look at the atomic number, 6 is equal to something minus 1. And that something is 7. So 6 is equal to 7 minus 1. So during beta minus decay, the mass number stays the same, but the atomic number increases by 1. But how does that really happen? In fact, in beta minus decay, a neutron decays into a proton and an electron. This is our decay equation. And just like before, our mass numbers add up perfectly, as do our atomic numbers. Here we have an example of a beta plus decay. Beta plus is shown by this symbol here. Try and complete the equation. Pause the video and have a go. So, in order for our mass number equation at the top to be satisfied, this number here would be equal to 0, because 18 is equal to 18 plus 0. And below, for the atomic number of oxygen would be 8. And that's because 9 is equal to 8 plus 1. So during beta plus decay, the mass number stays the same and the charge decreases by 1, or the atomic number decreases by 1. But what really happens during beta plus decay? It's similar to beta minus decay, but slightly different. In this case, a proton decays to form a neutron and a positron, also known as a beta plus particle. We don't need to learn the finer details about this, but we just need to know the basic equation. So here, a proton decays to form a neutron and a beta plus particle, or a positron. And a positron is simply a positive version of an electron. And just like before, our mass numbers add up, as do our atomic numbers on the bottom. And finally, we have an example of gamma decay and neutron emission. These are the final two equations we need to touch on. Pause the video and see if you can fill in these blanks. So, as we know, gamma is part of the EM spectrum, the electromagnetic spectrum, and it doesn't have any charge and it doesn't have any mass. Therefore, our mass number is 0. So based on this, the atomic number remaining would be equal to 43. Below that, our neutron has a mass of 1, and as it has 0 protons, the atomic number at the bottom here would be equal to 4. So during gamma decay, the mass number and the atomic number remain the same, but in neutron emission, the mass number decreases by 1, but the charge or the atomic number remains unchanged. This is a very quick run-through of some nuclear decay equations. I hope you found this useful. If you have any questions, please do ask.